data that will be presented by Dr. Alfonso Lopez. Alfonso, please.
Hi everyone, I'm Alfonso from the University of Juan, more specifically from the Computer and Graphics group. So I will be presenting the paper entitled 3D Tools for Building Inspection and Thermal Use. Oh! I was in front of you here. Okay. I will be presenting the work entitled 3D Tools for Building Inspection from Thermal UAS. Okay. So in this case we're using the goals of this work is to generate a 3D dense thermal point cloud. Our goal is to generate the point cloud rather than analyzing the point cloud itself. So we provide just a framework to generate the point cloud. In this case, we use thermography, which is one of the main data sources in remote sensing, and it is a non-invasive passive technology that allows us to capture information regarding temperature on surface. So in this case, it captures reflectance and translates it to temperature. So, what does thermal image represent? In this case, we only have images, and each pixel has a temperature which is represented as a digital number, raw data. So we can translate the digital number to temperature. The main problem of thermal data is the low resolution. So we have images maybe like 600 per 500. So in comparison with RGB information, we have like 2 centimeters per pixel in RGB. And in thermal data, we have nearly 5 centimeters. So the thermal data has less resolution. Also, thermal sensors present more defect, not only geometrical, which can be corrected, but also regarding the reflectance. For example, they are blurred, smoothed out, so they are more challenging in terms of reconstructing a 3D point cloud. Some of the disadvantages can be, let's say, reduced. For example, using a drone. In this case, we can, for example, reduce the altitude, so we have more centimeters per pixel. But others cannot be corrected, for example, the blur, the smooth out. So what is thermography used for? In this case, we have building inspection, which is the goal of this work. We have also fire detection, plant disease detection, and it is also used, for example, for vehicles, for night vision. And in the case of building inspection, let's say that temperature is a result of heat, airflow, and moisture. So in this case, we can use it mainly for detecting water leakage, for detecting heat leakage, so it can help to determine or to provide a quality measure for a building. Also, it tries to detect the insulation problems on the building, so we can correct it, for example, in this image. So, we can also use it for maintenance, so this type of fault doesn't occur. In this case, if we need to survey a building, we can either do it manually with handheld device. The main problem is that it is time consuming, but of course we can do a real-time analysis to identify the building fault. Otherwise, we can do it automatically with drones, robotic platforms. The main problem is that they return a large data volume, so we need to analyze it later. So we get something like that, just a folder with gigabyte of RGB and thermal imagery. In this case, for this work, we use a drone, the DJI 300 RTK, along with a dual sensor device which has RGB and a thermal camera. So, the thermal camera in this case retards low resolution images, and also I will also like to highlight that the image can be saved in three different formats. In the first case, DPG, we only have normalized values, so we can reconstruct the point cloud using this format because it is values in 0 and the maximum value. In diff, we get the temperature value, and finally the radiometric format retards both the DPG and the temperature, along with the intermediate parameters that allow us to process the temperature and to correct it, for example. So, in this work, previous work has managed the reconstruction of 3D thermal point cloud using commercial solutions such as Pix4D, Metashape. They use, in their core, they use the algorithm called structure from motion, SVM, which is based on finding feature within image. We can just correlate different features, different pixels in a sequence of image, so we can extract the 3D information of the environment. The main problem is that this type of algorithm fail with repetitive patterns, for example in buildings, and of course in blur imagery like thermography. So this is an example of point cloud reconstructed with SVM that fails in vegetation with repetitive patterns. So this is another example with the University of Juan. In the RGB point cloud, it doesn't have significant fault. It retards nearly 50 million points. And in the case of the thermal point cloud, you can see that the number of points is much lower, 4 million points, and also the reconstruction is much worse. In this case, there is a lot of holes. Also, another approach is to just reconstruct, for example, the RGB point cloud with SVM that doesn't have any fault. And later we can just project the thermal imagery into this point cloud that doesn't have fault. So the approach is to, let's say, register RGB and thermal imagery, and just to project the thermal imagery then into the point cloud. The main problem is that it also needs to correlate RGB and thermal imagery by identifying features, which is also challenging in, for example, in vegetation, buildings, etc. What we propose is to use a different algorithm, the non-correlation coefficient, ECC. In this case, it doesn't work finding features. What it does is to find the optimal position, the maximum correlation, and it tries to move, for example, the thermal imagery into the RGB and tries to find the position which had the maximum correlation. So it also works with images in different spectral intervals. So we could get something like that, which could be the position with maximum correlation. So from that, with this previous dataset, we get something like that, for example, with thermal imagery registered into the RGB imagery, and this is the case for other type of surveys. So using this approach, we get the result, the number of points here. In this case, this is our method with the starting thermal imagery, and this is the commercial solution, Metashape and Pix4D. However, instead of using the starting thermal resolution, we can increase it. Otherwise, we don't need to generate a dense RGB point cloud. I mean, we are generating just an RGB point cloud, for example, with 90 million points, but the thermal resolution is much lower. So, if we use the starting thermal resolution, we are losing a significant number of RGB points. So, what we do is to just increment the the thermal resolution. Of course, we are interpolating information, but we are also generating a point cloud with this much denser. And using this second approach with a higher resolution, we get, for example, 80 million points, while the best commercial solution, beta site, only achieves 20 million points. Also, we improve this solution by using the OpenGL framework, which allows us to improve the rendering of the point cloud. In this case, we are only rendering, for example, the nearest point, the nearest RGB point for each pixel. But of course, this approach generates like a noisy point cloud in terms of rendering. I will check. Look this one. This is the first approach. It only renders the nearest point. Instead, what we can do is to render the nearest point, but to also take into account in the color the neighborhood. So we are aggregating the color from point near to the first one. Using this approach, the rendering, which is the main goal of this work, is significantly improved. Later, we also consider the occlusion, just to avoid assigning thermal information to points which are occluded, which are background point, and are not visible from a thermal viewport. So we get something like that. This could be the final thermal point cloud. And also, all this process is a time-consuming task. So what we also do, what we also did, is to translate all this pipeline to the GPU, the graphical processing unit, just to parallelize the method. Using this approach, the time for our method is like that, nearly 2 minutes, and the commercial solution offers this time. Using a higher resolution, we generate also a denser point cloud. The time, of course, is a bit increased, but it is still lower than meta-site resolution. So, as a conclusion, we managed to generate a 3D dense thermal point cloud. We also improved the response time using the GPU. Of course, it is appropriate for generating thermal point cloud of buildings with repetitive patterns, etc. So, thanks everyone. Thanks everyone, and if you have any questions.
Thank you, Alfonso, for your very interesting presentation. Any questions? Please.
I have one. Thank you very much for your presentation. So about the structure from motion, typically is a technique that is used to more or less to do reverse engineering, more or less something. Can be used also for that, for reverse engineering. The structure from motion, we take several pictures and then we reconstruct the component using several points that are references in the pictures and so on. Here in your work, what is the error that you are detecting in your measurements from the buildings in centimeters or meters? Do you have an idea of that?
Do you mean in the reconstruction of? Do you mean in the reconstruction process? Or?
Yes, after in the final model.
The error is what we do is to, instead of using SVM with the thermal imagery, we perform it in the RGB imagery. So the error is just the error obtained reconstructing the RGB point cloud. What we do is to project the thermal imagery into the RGB point cloud that we know that doesn't have errors and these things. Because using SVM in thermal imagery, it has point cloud with holes, with 3D geometry, which is badly calculated, etc. I don't know if that is.
Yes, because my experience in the past is that with regard to 3D, for instance, we do not have enough precision for mechanical components. So probably your method is better than this.
Using RGB imagery, we will obtain more accurate point cloud. So
okay,
it is actually.
Thank you.
Yes.
Thanks for your presentation. Did you perform any comparative study between the method that you used, the thermography camera, and also the results from the 3D laser scanners?
Oh, we don't have a sensor like that. We didn't have a sensor like that, so we couldn't compare it because we did the surveys only with RGB and thermal information. But yeah, it will be nice to compare with the laser. In fact, we have now a LiDAR sensor, so we would like to project, for example, thermal imaging hyperspectral on the LiDAR information. But we need both sensors to compare the result.
Other questions? I have one, if you do not mind. Perhaps it's not obvious and it's irrelevant, but external temperature would affect the sharpness and nitidity of the pictures you obtain with your external temperature, environment temperature.
Yeah.
Summer, winter.
Yeah, it has a lot of influence in the temperature, and you can read books on the influence. I mean, we are just reconstructing the translated digital number into temperature, but yes, you can correct the temperature. It is another challenging work because there is books writing about that, about rectifying, and you have to take into account that maybe the most optimal conditions are, for example, a cloudy day, not a sunny day for measuring, for example, the external building, and so on.
Thank you so much. Next presentation will probably last one.